What's up, everyone? Welcome back. So, over the past 5 lessons, we've built up this entire understanding of transformers, right? We learned about the attention layer, the most crucial component. And you might be thinking, okay, we got attention figured out, we're done. But one more critical piece we're missing. Today, positional encoding. And here's the thing. Even with the attention mechanism, even with all that power, without positional encoding, the transformer cannot work. Attention is crucial, yes, but positional encoding? Just as important. So let's figure out why. Even after mastering attention, we still need this one more ingredient. Let's go. All right. Before we jump into the new stuff, before we tackle positional encoding, we gotta do a quick review. So if you've been following this series, and if you haven't, links are down in the description, go binge them. We've covered a ton of ground already. Lesson 1, Transformer Architecture Basics. Lesson 2, Attention Inputs and Outputs. Lesson 3, Query, Key, Value, the Holy Trinity. Lesson 4, the actual math behind attention. Lesson 5, multi-head attention and feed-forward networks. We've built this entire understanding piece by piece. But there's one critical thing we haven't talked about yet. And that's what today is all about. Okay, so let me show you the bird's eye view of how a transformer actually processes stuff. We start with some input, could be anything. Then we hit the chunker, also called a tokenizer. This breaks everything into little pieces. Then those pieces, or chunks, go into an embedding layer, which turns them into vectors, basically just numbers the computer can understand. Then we hit the transformer block. This is where the magic happens. We get these context-aware embeddings on the other side. Cool, right? Let's use our comic strip as a real example. Here's our input, right? 4 panels. Dog says, "I'm hungry." Food appears. Dog's eating. Dog's happy. Simple story. We all get it. Right now, this is just raw input. The transformer hasn't touched it yet. So let's see what happens when we start processing this thing. We've gone through the chunker, the tokenizer, and now we've got our 4 chunks all nicely separated. Notice they're labeled 1, 2, 3, 4. Looks good, right? These are the numbers we can keep track of the order with. So now we've hit the embedding layer. And check this out. Each chunk has been turned into a vector. See these colorful bars? Each one represents the meaning of that chunk. The first row? That's dog hungry. The second one? That's food. You get the idea. So these embeddings capture what each chunk means. The semantic meaning, the content. So let's say we send these embeddings through the transformer block, and we get these on the other side. Notice something? The colors are all different now. They've been mixed and matched. This is actually super cool. Each output vector now contains information from all the inputs. The first one knows about the dog, the food, the eating, and the happiness all at once. The transformer has created these rich, contextual representations. Transformer block consists of 2 stages. Stage 1, multiple attention heads working in parallel, each focusing on different stuff. Stage 2, everything gets combined and goes through a feed-forward network. We've already covered this in detail in Lesson 5. So I won't bore you with all the math again. But here's what I do want you thinking about. During all of this processing, all this attention, all this combining, is the transformer keeping track of what came first, second, third? The answer is no. And that's a problem. Everything we've been building, the embeddings, the attention, all these transformer blocks, they have a major flaw. The chunk order disappears. That's big deal. We have to do something. All right, review's done. You guys are up to speed. It's time to dive into the new stuff. Positional encoding. Let's go. Check this out. This is from the original Attention is All You Need paper, the paper that started it all. See these pink boxes at the bottom? Positional encoding on the left, positional encoding on the right. They're at the very base of the architecture. What does positional encoding do? Imagine you're a sniper. You see a target through your scope. What's the first thing you need to know? Where is the target, right? The position, the location. If you don't know where the target is, you can't hit it. Position is very important. Same deal with transformers. Transformers need to know where each chunk is in the sequence. Without knowing where things are, the transformer is shooting blind. And that's exactly the problem we're solving today. Let me show you some examples. Let's look at some actual examples. Starting with language. Michael loves Hannah and hates Kathy. Okay, clear story. Michael's got some relationship drama going on. Now what if we just swap token 1 and token 3? Hannah loves Michael and hates Kathy. Yo! The meaning completely changed. Now it's Hannah who loves Michael, not the other way around. Same words, different order, totally different story. And what if we shuffle everything? Loves Hannah and hates Michael Kathy. This doesn't even make sense anymore. The meaning is completely broken. So here's the takeaway. In language, order is critical. The position of each word matters. Okay, for language, we get it. Order matters. What about images? First, at the top row, we have our comic strip in the right order. Happy Cat approves. The story makes sense. However, at the bottom row, I shuffled all the panels. Now it's chaos. The confused cat is like, what on earth is happening? Same panels, same dog, same content, but completely shuffled. The story is destroyed. Vision transformers face the exact same problem. Now let's talk music. This is one of my favorite examples. Here's do, re, mi, fa, sol. Look at this beautiful ascending melody, each note in the right place. You can hear the melody, right? It's perfect. Now I'm gonna shuffle these notes. Sol, re, fa, do, mi. Random positions with question marks everywhere. What? This is not a melody anymore. This is just random chaos. No melody whatsoever. Same notes, but different order. Completely different music. And guess what? Music transformers, yes, they exist. Need positional information for the exact same reason. Are you starting to see the pattern here? Okay. So we've seen language, images, music, order matters in everything. But why does the transformer lose this information? Let's look at what's actually happening. Here's our pipeline again. Input goes through chunker, embedding layer, and then, bam, the transformer block. And inside here, the attention layer is what's causing the problem. Look at this formula, softmax of Q times K transpose, divided by square root of dk times V. This formula is mostly matrix multiplication. And here's the thing, matrix multiplication involves summation, and summation is commutative. What does that mean? Let me show you. Here's a simple example. We've got two vectors, x1 and x2. We take some weights, a1 and a2, and we compute a1 times x1 plus a2 times x2. Now watch this trick. a2 times x2 plus a1 times x1 yields the same thing. We get the same results. Because addition is commutative, you can flip the order and get the same sum. A plus B equals B plus A. That's basic math, but it's causing a huge problem here. So here's what the cat figured out. The cat's having a light bulb moment. x1 and x2 must deliver position information in order to figure out the order based on the same sum. In other words, we need some mechanism that injects position information into each chunk embedding. We've identified the problem. Attention mechanism uses summation. Summation is commutative. And the commutativity causes losing the position of each chunk. We need a way to inject position information into our data. But how? Alright, so what's the goal here? What are we actually trying to achieve? Look at this. Michael as token 1 goes through the embedding layer and we get this yellow embedding. Now, same word Michael, but as token 3 goes through the same embedding layer and we get the same yellow embedding? No. This is the problem. If Michael at position 1 and Michael at position 3 produce the same embedding, the transformer can't tell them apart. It's like having identical twins with no name tags. We need different embeddings for different positions. That's the whole point. Here's what we want. The embedding for Michael at token 1 should not equal the embedding for Michael at token 3. That's what we need. Same word, different position, then different embedding. Now the transformer can tell, oh, this Michael is at position 1, but that Michael is at position 3. That's the goal. Different positions must produce different embeddings. This property helps attention layer figure out the context coming from the order. Exactly. Remember, the attention layer is trying to understand, what does this sentence mean? What's the relationship between words? What's the context? And context depends on order. If the embeddings are different based on position, the attention layer can figure out, aha, this word came first, that word came second. So the meaning is this. Position-aware embeddings give the attention layer the information it needs to understand order-dependent context. Okay, this is super cool. Check out what's actually happening. The chunks come in, and they go to two places simultaneously. Path 1, normal embedding layer, which creates position-independent embeddings. This captures what the token means. The semantic content. Path 2. Positional encoding layer that creates position-dependent embeddings. This captures where the token is. Then, boom! The combiner merges them together, and we get position-aware embeddings. Now you know what and where. Complete information. That's genius right there. See this positional encoding layer we just talked about? It turns out there are many different ways to implement this thing. For example, Method 1, Sinusoidal Position Embedding. This is the original method from the Attention is All You Need paper, which uses sine and cosine waves. Method 2, Rope, Rotary Position Embedding. This is what modern models like Llama use. Rotating vectors in high-dimensional space. Method 3, Alibi, Attention with Linear Biases. Even newer approach with adds biases directly to attention scores. All three solve the same problem, injecting position information, but they do it in different ways. People are still finding better ways to do this. Let me show you the final architecture one more time. Chunker, embedding block, and one transformer block. This transformer block doesn't just run once. It gets stacked and repeated many times. In modern models, even thousands of transformer blocks stacked on top of each other. We're covering the full stack of transformer architecture in the next episode. See you there.